Good day, esteemed researchers and curious minds tuning in from around the globe. We're here to delve into the fascinating world of scientific language models with our paper, Galactica, a large language model for science. This groundbreaking research explores how language models can revolutionize the way we access and process scientific knowledge, breaking through existing bottlenecks. Stay tuned as we unravel the potential of language models to absorb vast amounts of technical knowledge and perform tasks that were once solely the domain of human specialists. Let's embark on this scientific journey together. The traditional methods of accessing scientific knowledge have been heavily reliant on human effort, leading to a bottleneck in knowledge throughput. The dominant paradigm of storing and retrieving information has its limitations, particularly when it comes to reasoning, combining, and organizing information. Moving on to the problem statement. The current bottleneck in knowledge tasks is the availability of high-quality, step-by-step datasets. It's important to note that language models, as they are now, will not perform tasks like humans until they undergo an architectural change that supports adaptive computation. This is a key area for future research and development. Our research has revealed some key highlights that underscore the potential of language models in scientific knowledge absorption and application. Firstly, we found that language models can effectively absorb technical knowledge, including LaTeX equations and chemical reactions. This capability extends to outperforming tuned, sparse, and dense retrieval pipelines in citation prediction tasks. Secondly, language models have shown the ability to compose a curated knowledge base, excelling in knowledge-intensive question-answering tasks. This includes learning tasks like IUPAC, naming through self-supervision. Furthermore, we've been able to formulate drug discovery tasks in a natural language prompt, demonstrating the versatility and potential of language models in scientific applications. These findings open up exciting new avenues for the use of language models in scientific research and discovery. Our research delves into the potential of language models to serve as a bridge between scientific modalities and natural language. We've used a variety of datasets in our exploration, including those from the fields of chemistry and biology. We've also incorporated data from NASA's Exoplanet Archive, PubChem Compound, UniProt, and RefSec Genome. These diverse datasets have allowed us to test and demonstrate the versatility and adaptability of language models in handling complex scientific knowledge. Let's delve into the traditional way of accessing scientific knowledge. For over half a century, we've been relying on a store and retrieve paradigm. While this method has served us well, it does come with its limitations. The most significant of these is that the reasoning, combining, and organizing of information still heavily depends on human effort. This reliance creates a bottleneck in knowledge throughput, slowing down our ability to process and utilize the vast amounts of information available to us. Now imagine a model-machine symbiosis, as depicted in the figure, where we can overcome these limitations. This is the exciting direction we're exploring in our work. We're proposing a shift in how we access scientific knowledge. Instead of the traditional store and retrieve paradigm, we're looking at language models as a potential game changer. These models can disrupt the status quo, providing a fresh, more efficient interface for knowledge access. The existing paradigm has its limitations. It struggles with reasoning, combining, and organizing information, and we believe there's a vast untapped potential in language models that we can harness. Why is this important? Well, language models have shown an impressive ability to absorb large bodies of scientific knowledge. They can even take on tasks that, until now, have been the exclusive domain of human specialists. This opens up exciting possibilities for the future of knowledge exploration and scientific discovery. Our proposed method utilizes a working memory token approach, which has demonstrated strong performance on mathematical benchmarks. This approach not only bridges the gap between scientific modalities and natural language, but also disrupts the traditional paradigm of accessing scientific knowledge. We've applied this method to a variety of datasets, including those from the fields of chemistry and biology. Specific datasets include NASA exoplanet, PubChem compound, UniProt, and RefSec genome. The key insight from our work is that language models have the potential to revolutionize how we access and process scientific knowledge. However, a significant challenge remains: the need for high-quality, step-by-step datasets. This is the current bottleneck that we need to address to fully unlock the potential of language models. We propose a novel use of language models as a new interface for accessing knowledge, disrupting the traditional store and retrieve paradigm. Our methodology employs a working memory token approach, which has demonstrated strong performance on mathematical benchmarks. This approach allows language models to absorb technical knowledge, such as LaTeX equations and chemical reactions, and apply it in a step-by-step reasoning manner. Furthermore, we explore the potential of language models to act as a bridge between scientific modalities and natural language. For instance, our model, Galactica, has shown the ability to learn tasks like IUPAC naming through self-supervision. This opens up exciting possibilities for automating tasks that are currently human specialisms, and we look forward to seeing how this can be further developed. In our research, we utilized a variety of datasets, including those from chemistry and biology. Notably, we used NASA exoplanet, PubChem compound, UniProt, and RefSec genome. These datasets provided a rich source of information for our language models to learn from. We evaluated our results based on performance across various tasks and benchmarks. Our language models demonstrated an impressive ability to absorb technical knowledge, including LaTeX equations and chemical reactions. This absorption of knowledge scaled smoothly with the size of the model, showing the potential of these models to disrupt the traditional store and retrieve paradigm of accessing scientific knowledge. In conclusion, our research shows that language models can be powerful tools for exploring scientific literature and knowledge, and we look forward to seeing how this technology evolves in the future. Language models have shown remarkable performance in several areas. They outshine both sparse and dense retrieval pipelines in predicting citations, demonstrating their potential in exploring literature and scientific knowledge. Furthermore, they can compose a curated knowledge base, excelling in knowledge-intensive question-answering tasks. The potential of language models extends beyond these tasks. They have proven to be powerful absorbers of vast amounts of scientific knowledge, including complex technical information like LaTeX equations and chemical reactions. Moreover, they can perform tasks that have traditionally been the domain of human specialists. This opens up exciting possibilities for the future as we continue to explore and expand the capabilities of these models. The current challenges we face include the lack of high-quality datasets that provide step-by-step solutions, which are crucial for training our models. Additionally, we need to consider architectural changes that support adaptive computation, as this will allow our models to perform tasks in a manner more akin to human cognition. Now, let's talk about the potential of large language models, or LLMs. These models can serve as a bridge between scientific modalities and natural language, enabling a more intuitive interaction with complex scientific knowledge. For instance, tasks like automatic protein annotation, which are traditionally labor-intensive, can be effectively handled by these models. This opens up a new realm of possibilities for scientific research and discovery. Our research has yielded some key technical results. Firstly, we found that language models have the ability to absorb technical knowledge. This includes complex elements such as LaTeX equations and chemical reactions. Secondly, in citation prediction tasks, the language model we studied outperformed others, demonstrating its potential in exploring scientific literature. Furthermore, the model was able to compose a curated knowledge base, excelling in knowledge-intensive question-answering tasks. This shows its capability to organize and combine information in a step-by-step reasoning manner. Lastly, we discovered that the model could learn tasks like IUPAC, naming through self-supervision. It was also able to formulate drug discovery tasks in a natural language prompt, showing its potential in bridging scientific modalities and natural language. These findings highlight the strong potential of language models in taking on knowledge tasks that are currently human specialisms. Our research indicates that language models have the potential to revolutionize the way we access scientific knowledge. Instead of the traditional store and retrieve paradigm, these models can absorb and organize large bodies of knowledge, performing tasks that are currently human specialisms. However, there are challenges to overcome. The availability of high-quality, step-by-step datasets is a significant bottleneck in improving language model performance. Furthermore, to truly mimic human-like task performance, these models require an architectural change that supports adaptive computation. This is the exciting frontier we're exploring. As we draw our discussion to a close, let's take a moment to reflect on the key contributions of our research. We've introduced a novel approach to accessing scientific knowledge using language models, a significant shift from the traditional store and retrieve paradigm. Our work has shown that language models can absorb technical knowledge, such as LaTeX equations and chemical reactions, and perform impressively on tasks like citation prediction and knowledge-intensive question answering. Take a look at the figure on the right. It illustrates Galactica's ability to use its knowledge of chemistry to assist with the IUPAC naming task. The model attends to the part of the molecular graph associated with the group name at each stage of prediction, demonstrating its potential to bridge the gap between scientific modalities and natural language. In conclusion, our research opens up exciting possibilities for the future of scientific knowledge access and exploration. Our research has led us to several key takeaways. Firstly, language models have the potential to revolutionize how we access scientific knowledge, disrupting traditional store and retrieve methods. Secondly, the capabilities of these models scale smoothly with their size, offering significant advantages over search engines. However, we've identified a bottleneck in the availability of high-quality, step-by-step datasets. To perform tasks like humans, language models require an architectural change. This opens up new avenues for future research, including the exploration of a larger corpus and the development of a layer for verifying the accuracy of language model generations. Lastly, we've recognized the need for further research on the best procedure for incorporating new knowledge into the model. We also see potential in retrieval augmentation to complement the flexible weight memory of the transformer. These findings guide us towards the next steps in our journey to unlock the full potential of language models.